Unit 9, Worksheet 1, Qualitative Impulse Momentum, Problem 2. Now for this problem, which has the greater change momentum? A 50-gram clay ball that strikes a wall at 1 meter per second and sticks, or a 50-gram super ball that strikes a wall at 1 meter per second and bounces away from the wall at 0.8 meters per second? Well, one thing that I'd recommend we do is, as always, start off by drawing a picture of what is occurring. So I'm going to start off with the clay ball. So for my initial condition, we have a ball that has a velocity traveling this way. Then at my final condition, it hits a wall, and then it ends up with a final velocity of 0, representing this right here. So in this case, since I'm just looking at the ball, I want to figure out what the change in momentum of the ball is going to be. So in order to do that, what I'm going to do is, if I'm looking at the change in momentum, I am looking for the momentum at the end, the final momentum, minus the momentum at the beginning, or the initial momentum. I know for both of these, to calculate my momentums, it's mass times our velocity. The mass is going to be constant, so the only thing that's changing is our velocity. So once I have that, I just need to plug in the values that I know. For example, I know that I have a 50-gram clay ball, or a 0.05 kilogram clay ball. And I know initially it was going to be moving at 1 meter per second, but when it sticks to the wall, the final velocity is 0 meters per second. Minus, I still started off with that mass of 0.05 kilograms, times my initial velocity of 1 meter per second. So for the clay ball, the change momentum is 0 kilograms times meters per second minus 0.05 kilograms meters per second. 0 minus 0.05 is negative 0.05 kilograms times meters per second, and that is going to be the change in momentum of the clay ball. We're going to compare that to the change in momentum for the super ball. So for the initial condition of the super ball, it will actually look pretty similar. It is traveling at that initial velocity of 1 meter per second. So I'm showing that these two visually look the same. They're equivalent. They're traveling at the same speed, and they're actually traveling in the same direction from the way I've drawn it, and also they have the same mass. Now when I'm looking at the final condition though, it's still going to hit a wall, but what ends up happening is now the ball ends up traveling in the other direction. And it's traveling in the other direction, it bounces back with a smaller speed than what we hit the wall with. So I'm drawing that arrow slightly smaller. To calculate the change in momentum of the super ball, same process, final momentum minus initial. Mass times the final velocity minus mass times the initial velocity. The 0.05 kg times are now going in the left direction, 0.8 meters per second, and because it is traveling left, I'm saying that's going to be a negative sign. Minus our 0.05 kilograms times our 1 meter per second. When I set this up this way, instead of starting off with my final momentum as 0, I end up with a final momentum of negative 0.04 kilograms times meters per second, minus, still minusing that 0.05 kilograms times meters per second. Negative 0.04 minus 0.05 will give us negative 0.09 kilograms times meters per second. And this is our change in momentum for the super ball. Well, when I'm comparing these two, the change in momentum for the super ball is negative 0.09 kilograms times meters per second, whereas the change in momentum for the clay ball is negative 0.05. Well, the bigger number is going to be 0.09, even if it is negative, because it has a greater magnitude. So that is going to be a greater change in momentum for the super ball than we have for the clay ball.